All right, let us continue. So last time we discussed encoding for integers, right? And we talked about bits, right? And the fact that every integer is essentially a sequence of bits, and those bits can be seen as an integer value, right? So I would like to make these bits more real to show you that they actually exist, and we're going to learn about bitwise operations. So I'm going to start with a file called bits.c. So we do our usual stdio.h int main, and let's say we don't take, should we take arguments here? I don't want to confuse you further. We're going to read a number of. Let's just work with constant values for the beginning, and we're going to see later how we go about reading these values from the keyboard. So I want to show the bits from this number, right? Okay, so there would be a very simple arithmetic way to do that, right? How would that be? We divide by 2, right? And we take the remainder, and that's the last digit, right? So computing the reverse digits would be very simple arithmetically. Though we haven't learned arrays, we'd have to put all these elements into an array, then reverse the array, and then that's what we print out, would be the binary representation, right? But we're not gonna take that. We're going to take a different approach. We know that the integer has 32 bits, all right? And we're going to learn a new instruction. Less than 32 I plus plus, okay? So what we're going to do here is we're going to say if a ampersand 1, and actually I'm going to go in the opposite direction. I'm going to go from 31 to 0, and I'm going to decrease. I minus minus means decrease every time by 1. And I'm going to say I shift to the left I bits. So if this number is non-zero, and let's make it very clear that we're saying here not equal to 0, right? What does this operation do? It performs a bitwise conjunction. So it takes every bit from A and every bit from this number, right? And let's see, what is this number? If I take the number 1, this is a number that has 31 zeros, 31 bits of 0, and the last bit is 1, right? And then this operation, so the number 1 is a number that has 31 zeros, and the last digit is 1, right? The last binary digit is 1. So now this operator shifts to the left by whatever count I provide here. So since I have a single 1, that 1 will go shifted, right? So I'm going to produce numbers that have a single bit in some position, in the position given by this I. Initially, this number is 31, so we're going to shift this 1 bit 31 times till it reaches in the first position, right? So it's a number which has only 1 bit. The first bit is 0, and it has 31. The first bit is 1 and has 31 bits of 0. Is that clear? And then when we perform bitwise conjunction, the 1 that is in the first position conjoined with whatever is in the first position of A is going to be that number, right? So whenever I have 1 and x, that's going to be equal to x, right? 0 and x, so 1 and x is x, right? And 0 and x is 0, right? So we're going to essentially check whether the first bit of A is 1. If this is true, it means that the first bit is 1. So I'm going to say put char 1. Put char is a library function that just puts a single character out. Else, I'm going to say put char 0. All right? So I claim that this will give us the binary encoding of whatever the value of A is. Okay? So let's make this even more apparent. So let's say my number is, I'm not going to use 32 bits because there's too many of them, right? I'm going to say 1101, right? So what are the values of this expression going to be, right? So at some point, I'm going to get, I'm just going to write underneath because it's easier. At some point, initially I'm going to get 1000, then later I'm going to get 0100, right? So this would be when I equals 4, I equals 3, sorry, I equals 3, I equals 2, right? 0010 for I equals 1, right? Is this clear? We're looking at this expression, right? So let's say I goes from 4 to 0. And it's going to be 0001 when I equals 0, right? Now if I'm looking at this operation, when I take this number and this number, what's going to be the result? It's bit by bit, right? So for the first position I get the 1, then I get 0, 0, 0, right? So it's going to be 1, 0, 0, 0. Since it's non-zero, since this number is non-zero, we're going to output A1. So I'm going to record the output here. Then I'm going to take this number and this number. What's going to be the value? Well, for the first position, 0 and 1 is 0. For the second position, 1 and 1 is 1, right? For the third position, 0 and 0 is 0. For the fourth position, 0 and 1 is 0, right? So I'm going to get 0, 1, 0, 0, the same as this, right? So that is still not 0, so I'm going to get a 1 on the output, right? Going here. So the first number and this guy. So we're going to get 0, right? And finally, the first number and this guy. We're going to get a 1 again, right? So you see by this process, we're essentially replicating this, but, right? We know that internally the number is 1, 1, 0, 1, but for us this is 13, right? Right? So 13, we don't know what the binary encoding is, and we're trying to find it out, right? So we're trying to replicate the binary encoding. Does it make sense? So let's execute this. I'm going to remove this stuff, and let's see that we're getting the correct. And actually, let's start with 13 here. right? So we're told that the precedence is ambiguous, so we need an extra round of brackets here. This is just a warning. All right? So it would be good to have a backslash n at the end. Okay, but you can see already that the number is 1101, right? The prepending zeros, the initial zeros, these zeros, they don't change the value. These zeros don't matter, right? Okay, and if you want to convince yourself, let's go to a more complicated number. Make sure that it works for arbitrary numbers, right? So we get the binary representation of that number, right? So the important lesson here is that the bits are real. They're not something esoteric. Okay? Now, for those who arrived late, normally, how would you do this in a different language? You would divide, in a loop, you would divide by 2 and take the remainder, and that would give you the reverse digits, binary digits of the number, right? So you would typically put them in an array, you would reverse the array, or you would use recursion to print them in the right order. All right? So we can actually try that. Why not? Just to convince yourself that it's the correct result. So the other thing that we're going to want to print is printf %d. Actually, we will want to say what do we want to say? Nothing. We want to just convert. So let's call this function called convert of 1, 2, 3, 4, 5 of 8. Sorry. All right, and let's write the function convert recursively. All right, so it's a function that doesn't return anything. So it's a function that returns void. And this is a new thing we are seeing. Int n. All right, so we're going to say convert if n not equal to 0, n not equal to 0, convert n divided by 2, and then put, actually we're going to say printf. We want to convert printf %d, and we're going to say n remainder 2, right? Is this clear that this performs the conversion? So what we want is to reverse, right? To reverse the printing. And we're taking advantage of the recursion to do that, right? So what are we going to do, right? If n is not equal to 0, first we convert. So we print n divided by 2, right? And we're taking advantage of the fact that n is equal to n divided by 2 times. Okay, so let's write it this way. 2 divided by 2 plus n %2, right? So this is true, right? But then multiplication by 2 is what? Is a shift, right? Very good. Some people don't know their bits. Right? So, and what is this? Remember, this is just one bit. So this is essentially juxtaposition. I take the digits from here, and I append the digit from here, and I get the number, right? So what is this guy doing, right? It's printing n divided by 2 in bits, and then it's appending the last digit, right? Does that make sense? All right. So now we should have the same result, right? And that should give us the sort of certainty that we're getting, we are doing the right thing. Oh, here too. Okay, so this is interesting now, right? Because you see, in the second method that we're having, these zeros don't get printed. So the second method is more economical, right? We're printing as long as we don't encounter the value 0, right? But this part is identical to whatever is the second number, the second binary number, right? Which tells us that our method for conversion is correct. The bits do exist. Let's try to do the opposite. Let's try to read, and I'm going to add, just to let you have a full-fledged program, I'm going to read the input from the keyboard, right? And I'm going to apply the same pattern as before, even though we haven't learned pointers, right? So you're going to just swallow this for the time being, without a lot of explanations. So remember, argv is an array of strings, right? The strings being the words that we put on the command line. And we have to convert those words into integers. So we're going to use scanf, and we want to read an integer into, we want to read an integer from argv of 1. So arrays start from 0, right? But the first element is the program name. I'm going to remind you of that in a minute. And then we want to read into A, which A has to be declared. Okay, so now we can convert this and it's actually, I need an array here. So please just swallow that for the time being. So now I'm going to say bits 1, 2, 3, 4, 5, right? And we can pass the value from the command line, right? This 1, 2, 3, 4, 5 comes from here. It's not a constant anymore, right? I can change this to anything else, right? And you can verify now that we were getting the same result. So we can write a large enough number so that we occupy all the 31 bits. Let's try to do that. This is becoming interesting because we probably exceeded. All right, there you go. So if we try to use a 2 here, no, it's still too large. Ah, okay. 5 is too large. 4. Then here's some. Do you understand what I'm trying to do? Oh, really? I see 7 here. I think I deleted too many. Anyway, so I was trying to get to a point where, but I could do that in a lot easier way. So I can do 2 to the power of 31, and I could take this number and put a 9 here. What? We'll never get it. It has to be negative. It has to be negative, right? And then we get a minus, so 7? No. You go and figure it out. Okay, I was trying to fill all the 31 bits. But it's quite obvious here, right, already, because these and these are identical, right? And it's clearly we have the right map. So is this clear? All right. So remember now that what are we learning here? We're learning quite a few things in a very small space, right? We're learning how to shift bits. All right, and shifting bits is tantamount to multiplying by 2 if we shift to the left, and tantamount to dividing by 2 when we shift to the right. All right? So the greater sign will shift to the right. Okay? The single ampersand means bitwise conjunction, bitwise AND. Right? So this happens bit by bit. And it works automatically between any kind of integers of the same size. It's integer specific. All right. There's a similar operator called OR. all right, which is a bar, single bar. These are not to be confused with the logical AND, which is double ampersand, and logical OR, which is double bar. All right, so this is the bitwise OR versus logical OR. So with logical AND, any non-zero value, logical AND any other non-zero value will yield 1, precisely 1. All right. Any non-zero value conjoined with a zero value will yield 0. All right. And it's commutative, so vice versa. And 0 will yield 0. With OR, it's similar. Any non-zero value or anything will yield 1. Any 0 or 0 will yield 0, right? And it's commutative. So I'm not going to insist much on those operators since they are similar to the ones we have seen in Python. All right, the conversion you have from here. So now let's try to do the opposite. Let's try to read the bits and convert them into the number. All right, read the bits from the command line. So I'm going to copy this bitread.c. So we're going to call it bitread. I'm going to open this file. All right, and we're going to modify. We don't need the convert function anymore. So I'm going to delete it. I'm going to continue to read from the command line, and I'm going to keep asking you to swallow this for the time being. Okay, so how would we, reading a number of bits, but by the way, actually we don't need to do that. We don't need to do that anymore, right? Because what we want is the string. So how would we go about converting converting a number of bits into the number itself, a sequence of bits into the number itself? I'm going to start with an A that is equal to 0, right? And then so think of the binary OR, the bitwise OR that we have discussed previously. Mm-hmm. But I want to use bitwise operations, right? Which typically are more effective, more efficient. So let's assume that the length of the string is always, the string is going to be in argv1. Argv1 is going to be my string, right? So actually I can say char star, and again, char star is a string for the time being, s equals argv1. So let's assume that this has 32 digits. All right? Actually, we shouldn't have. We should keep the convert, and I'll show you why soon. Let's leave it here. So let's say we have 32 bits for the time for starters. Let's just assume that, because it makes the problem so simpler, right? And let's just iterate 32 times for right. So if si equal 1, right? What do we want to do then? A bitwise OR actually, again, we have to start from 31. 1 account, 2, 0, and minus. Is that what we want to do? So the digit that I'm reading from the input is 1. And it's a character because we're reading a string, right? So whenever you see this guy here, this is a string, right? Previously, in order to make the string into an integer, we used scanf. But now we're going to just deal with the string. So what I'm going to type here is bit read, and I'm going to say 11100001110, and I'm going to have 32 of them. All right. So this 1 that appears here is going to be a character of 1, not the number 1, but rather character of 1, right? And now I want to clobber whatever bit is there in A into 1. How do I clobber it into 1? I do a bitwise OR with 1 shifted by I bits, right? So let's say that my number initially is 0. Four bits, right? So my first digit here is 1, right? So 1 shifted by 4 bits is going to be 1000, right? Actually 3 bits, because we're going up to 31 here. So this guy, bitwise OR, this guy is going to be, yes, 1000. Then let's say that my next number, so I do many ones, I reach a number of 0, right? A digit of 0, right? So what should I do? So let's say that my next guy is 0. What should I do? Well, this guy is already 0. So I can just leave it as this, right? But let's say it weren't 0. What could I do to clobber it into 0? Instead of doing bitwise OR, I should do bitwise AND, right? And I should do bitwise AND with what? With 1, 0, 1, 1, right? So remember that 1 and x is x. 0 or 1 or x is 1, right? 0 and x is 0, right? And then 0 or x is x, right? So these are general identities from Boolean algebra, right? So then if I want to impose a value, I can only use those operations that have a definite result, right? This has a definite result. So if I want to impose a 1, whatever x is, I want to impose a 1. So I have to use bitwise OR. Now bitwise OR has the nice property that if I use a 0, I leave the value unchanged, right? So what I want to do is impose a 1, but leave the rest unchanged. So I have to do a 1 where I want to clobber and 0 in the rest. If I want to clobber a 0, I can only go with that operation that gives me a definite 0 as a result, right? So this is my only choice. I have to use an AND. But now AND has the nice operation that when I use a nice property that when I use a 1, the value is unchanged. So what I want is in one position, whatever I have here, I want a 0. But in the rest of the positions, whatever I have here has to be preserved, right? So if I want to clobber a 1 into a position, I'm going to put 1 in that position and 0 in the rest, and I'm going to use bitwise AND, right? If I want to clobber a 0 into a position, sorry, bitwise OR, right? And if I want to clobber a 0 into a position, I'm going to put 0 in that position and 1 in the rest, and I'm going to use bitwise AND. Okay? So, though it is not necessary, I could do else A and equals, so I'm going to say 1i, but then I'm going to negate this, right? So it's not very easy to produce zeros, right? Numbers with many ones and a single 0. So then I'm going to produce a number with a single 1 and many zeros, and I am going to negate it. This negation is bitwise as well. So every bit gets complemented. Okay? Now, it so happens that we're starting from a value of 0. A is initially 0, right? A is initially 0. So this is redundant. But I'm going to leave it there because I want you to see that operation. Okay? So this, again, you have to swallow. And for maybe another session. So the next Tuesday, I'm going to reveal everything about pointers. So then it's going to be clear what's going on, right? But this is a string. S is a string, and then Si is the character on the ith position of that string. Okay. Now, so this is still kind of a wonky program. We don't like it that much because we have to input exactly 32 digits. Even if we have prepending zeros, we still have to input 32 digits, right? So I'm going to make sure that I get to column 32. All right. So I'm going to get this number. And A at the end is the value that we want. So what we're going to do is we're going to print it to see what the digital value is. Right? We produced an A that has the binary representation that we read from the keyboard. And then we're going to convert it back. And as we convert back, we should get exactly the same digits as in the input. And that will tell us whether the number is correct or not. The conversion is correct or not. Okay? So let's compile. And then let's see. Ah, wrong result. All right, so let's debug. So let me first delete this and see if this makes a difference. Oh, there is no semicolon. How come it worked? Oh, this is int. How come it worked? I think I didn't save previously. I think I didn't save previously. All right. So it's not working properly still because it ends in a 1. Ends in a 1. So is it reversed? It's reversed, right? So notice that this is reversed. Oh, okay. So you see SI is going down now because this I is going from 31 to 0, but here I would like the index to go from 0 to 31, right? So then we're going to create, we are going to create two indices. I'm going to have j equals 0, and I'm going to have here j plus plus. I'm going to say here that this is j, right? Should I save? Louder? So then j plus plus. No, now we just have an extra 0 here, right? Again? I should go from 31 to 0, right? Because if you put the 1 in the 0th position, then you can only go 31 times before you fall off the integer, right? So So we have an extra 0. Which is strange. So let's print. So C is for character, and let's see, verify that SJ is what we expect it to be. So reading 0, 1, 0, 1. All right, so we know that the conversion, this convert function, takes away the first 0, right? But then it adds this 0 here, which is not good. So the last number that we read is 1, 101. All right. And because we end in 1, this number should be definitely odd. I say here convert in. Let's see what are the values of I and J. Oh, they're no longer available, so that's declared here. Minus 1 and 32, which is correct. Right, so I was last times 0, right? So A or 1 shifted 0 times should be 1, right? Okay, if I say 32 here, doesn't make any sense. I don't know for the life of me what's wrong with this. Pardon? So j starts from 0, and right, so I could replace this with j less than 32. Should not make a difference. But it seems that what if I do only 31 digits? If I start from 30, now it's correct. So it's something to do with negative numbers. So when we do one, all right, so the first thing we want to do is print 1, 1, and that's correct. So this number is 1 shifted 31 bits. If I do it 32 bits, yeah, it will say that it can't, right? I'm shifting too many bits. So now the interesting thing is, if I say -1 bitwise and why is this? No, yeah, it's correct. It's correct. It's correct. So then why doesn't it work? So what I want to do here is put an OR. Yeah, of course, correctly. So then what's wrong here? 30. So if I make this 31, so the question is now what's wrong? But definitely this one is wrong because this one is even and this one ends with a 1. It should be what? Odd, right? So how come it's shifted by 1? All right, we'll figure this one out. I'll let you go. I'll send the correct code and the explanation as an announcement to the group, okay? Yeah, class dismissed.